So I'll go ahead and start recording. So in general, we're going to talk about eigenvectors today. Let's just call out some catch-up things. We'll start with that. Just some things that I've noticed on the midterm, some things that you should absolutely know how to do for your skills developed in this class. Now, I know I said previously that in many ways, linear algebra, this course is kind of similar to calculus, at least in Calc 1, where in Calc 1, almost every problem, you're going to want to take a derivative. The analogous to this course, at least up until about now, is that in most problems, especially if you have a matrix or a matrix determined by a linear transformation, you can row reduce. So row reducing in a lot of different problems is going to be a common tactic. Unfortunately, this also seems to be a crutch for many of you guys. Now, there's a few problems in the exam that row reduction wasn't necessarily the wrong thing to do, but it was completely unnecessary and completely waste of time. Like, it was a huge waste of time for a lot of you guys, and it just results in a lot of mistakes. So this is a higher level class, right? This is beyond calculus. And so I don't want you guys to have poor mathematical skills if you're only relying on row reduction and not understanding anything else we're really doing in this course. It's going to be hard for you to get a passing grade. So you've got to keep up with the material we're doing. Understanding linear transformations, general properties of what it means to be a linear transformation, especially the properties of linear transformations. And then these more abstract, these bigger concepts like injective, surjective, the rank and nullity theorem. You guys should have these in your tool belts, in your brain, for tools you can use to help solve problems. Because it seems like if I change the problem slightly and have any sort of problem that doesn't require row reduction, a lot of you guys are falling apart. And it's kind of a scary thing, especially with the basics. So for example, we saw things like this. Here, let's make it three-dimensional. T of ABC is equal to something like 3a plus 4c minus 2a minus 2b and minus c plus 6b. If you do not understand what this means by the end of the semester, I cannot give you a passing grade. That's kind of a solid rule now. Like, if you fail a problem like this and do not understand how to approach a problem like this, you're going to have to retake the course. Your linear algebra skills are just not adequate in terms of understanding the structures we're working with and understanding the mathematical notation that is going on. So I'm going to explain it, and I'm only going to explain it once because this is very elementary. It's stuff that's similar to things that have appeared in the homework problems. It's stuff that has appeared in the lecture. It's stuff that has appeared in the book. So there's a problem like this on the exam where we gave two linear transformations based on how they act on a given vector. And then the problem was to find the matrix associated with the composition of the linear transformations. And there was a lot of people who tried a lot of ridiculous things and showed a very poor understanding of what these A, B's, and C's were. People were trying to add X, Y, and Z and then make this into a matrix and then had like two sets of variables, and it was a little concerning. What does this mean? This means here. So let's just actually say this. So vector, the matrix of a linear transformation we find the image of our standard basis elements and then these guys are the columns. So this is the baby way to do it. It requires a very low level of understanding and mathematical thought. So you can compute each of these. What's T of 1, 0, 0? By the formula, our A is 1, B and C are 0. So that'll give us 3, a minus 2, and a 0 here. T of 0, 1, 0. B is now 1. Everything else is 0. So that'll give us a 0, a minus 2, and a 6. And lastly, our T of 0, 0, 1 is going to be equal to, now our C is 1, A and B are both 0. So we're going to have a 4, a 0, and a minus 1. All of these are now going to be your column. Column 1, column 2, column 3, and that's the matrix associated with T. That is the little bit more work, but it is tried and true and will get you the matrix associated with T. If you want a quicker way, you can essentially just eyeball it. I know we're going to have, especially because in the problem statement, if we say something like T is a transformation between R3 to R3, we know we're going to have a 3 by 3 matrix. And now our vector, it's a 3-dimensional vector with components A, B, and C. So I want a matrix acting on A, B, and C to get this same result. It's always going to be in this top column, top row is going to be the first row times our vector. We have 3 copies of A, 0 copies of B, 4 copies of C. So if I take this row and a dot product with that column, that'll give me 3A plus 0B plus 4C, first row. Here we have 2 copies of A, negative 2 copies of B, and 0 copies of C. Second row times my vector will give me minus 2A, minus 2B. Third row, careful of the order, but we have 0 copies of A, 6 copies of B, and minus 1 copy of C. That is the quicker way to come up with the matrix of a linear transformation when the linear transformation is explicitly described as such. And if you check, what's the column vector here? Same column vector. Column vector here. Column vector 3. Exactly like we computed. Any questions on that? So that fundamental, you guys got to know how to be able to come up with a matrix of a linear transformation from an explicit closed form expression like that, right? All this is a system of linear equations or a system of linear operations. And so coming up with the matrix corresponding to that, absolutely essential for this course. Some of the other ones were a little hard, but so like number 4 was this change of basis problem. That one's a little bit trickier because there's some understanding you gotta to understand how to approach the problem, and you're gonna struggle a lot understanding how to even approach that problem. If stuff like this is hard because you need to find the matrices corresponding to both the linear transformation as well as the change of bases transformations. Let's see. Anything else that I am seeing? Let me take a look. Let me go ahead and share the exam again. So this was exam 3. Just some things to be careful about. I think first one was good. First one was great. Most people, or at least, understand the definition of our rank and nullity theorem. For number 2, be careful. Make sure you guys are showing all your work and simplifying. You should simplify to the degree that we would expect in calculus, either Calc 1, Calc 2, Calc 3. So if I give you an angle theta, not only do you need to know what the rotation matrix is, but you should plug in that angle theta, and you should be able to reduce your sines, cosines, or tangents if they come up. Any trig functions evaluated on the unit circle, on things you can evaluate. Anything you can simplify, simplify. So make sure you're computing all of that stuff out. This guy we just talked about actually didn't change S, so S and T were the same matrix, so really you had to square that matrix. 4, you may want to look over these problems. This problem might show up again on the final. It probably will show up on the final. It's another very essential problem when we're looking at the linear transformation in regards to different bases. So very important. As well as this problem. This problem wasn't 5 and 6 weren't too bad. I think most people got some ideas, but I think some of the ways people were solving them was a little bit roundabout. For example, in problem 5, a lot of people tried to solve for the matrix of T. Now, funnily enough, a lot of you guys actually got it. Some of you guys tried to solve for the matrix of T, but didn't do it quite well. For those of you that did solve for the matrix of T, it was rather complicated the way you went about doing it, and plus the numbers didn't work out too well. You want to be careful with problems like this. This is a problem where you want to look out for the properties of linear transformations. Primarily in the sense that if I can take a linear combination of this vector v1, 2, 5, and maybe vector v2, -1, -3, -1, 3, and get a linear combination of those two vectors to arrive at this vector 0, 11, then I can perform the same linear combination on the image vectors. And it makes the computation much, much simpler. And you also want to be careful with attempting to solve the matrix of T, because I could give you maybe a transformation from R4 to R4 and only give you 2 of the vectors. If I only give you the image of 2 of the vectors, you're not going to be able to find the full transformation of T. So be careful with stuff like that. You got to have some extra tools in your tool belt, other than just trying to find the matrix, trying to row reduce this matrix. So try to keep up with some of the bigger theories and other techniques we have. Likewise for this problem, most people didn't do bad, though you got to be very clear on your justifications. Your justifications actually have to, 1, follow your work. So make sure you're showing all your work. And that reminds me on like this problem too. Make sure you guys are showing all of your work. There's a huge, huge problem with academic misconduct and cheating over this past year with having an online courses. So if I don't see any of your work, I'm not giving you credit. And so if you somehow arrive at the final answer and I don't see change of bases matrices, and I don't see appropriate multiplication of matrices or the formula for MBB, I cannot give you credit. So make sure you guys are showing all your work and justifying things appropriately. On this problem, okay, we've got a matrix, and a lot of people row reduced, and then sometimes people row reduced, but it's like you didn't quite know what to do with the row reductions. Some people got it. Some people were able to conclude either to make statements about the rank of T and then conclude whether or not T was injective based off of that and whether or not T was surjective based off of that. Some people row reduced and then just kind of, it almost seems like you guessed and you didn't fully justify. So unfortunately, I couldn't give you full credit. It's like you row reduced and then made a statement about injective or surjective that didn't quite follow. But in general, like, you don't quite have to row reduce here. at least for injective. Injective is a little bit quicker. I mean, injective, you can conclude that it is not injective. So why can it not be injective? Well, this follows from the rank and nullity theorem. Even without any computations, we know that the rank of T is at most 2, which means the rank is less than the dimension of the domain. So it has to kill off at least one dimension, which means the kernel is not 0, which means it's not injective. Surjective, you got to be a little careful of. You do want to make arguments about the rank. So some people try to claim that it's rank 2. Got to be careful, even though it's a matrix and it's a transformation from a 3-dimensional space to a 2-dimensional space, it is not necessarily rank 2. So your work has to justify that. So you can either row reduce or you can explicitly compute surjectivity. I think at least one student did that, where you pick a vector in the image, pick an AB, R2 vector in the image, and show that you can always find some vectors that map to it. So that's about as far as I've gotten. I've still got a grade 7, 8, and 9. So we'll see how those goes. If I have any more comments, I will let you guys know tomorrow. And then in terms of our exam on Friday, make sure you know how to do the things we've been talking about this week. 1, determinants. It's mostly all been determinants so far, but now we're going to start in on eigenvectors and eigenvalues, and we've got 2 days on this. We've got today and tomorrow. So there's going to be some eigenvector problems on the midterm, on the exam. So try to keep up. Eigenvectors and eigenvalues are a little complicated. When most people first learn them, they can be kind of tricky. And for these problems, I don't think row reduction, it'll kind of come up, but you got to be careful with it because it's going to come up in a similarity fashion where it's actually both row and column reduction simultaneously, row and column operations. So you've got to be careful with how you go about doing it. Determinants, though, hopefully aren't too bad. You should know all of the applications of determinants, what determinants tell us in terms of invertibility, in terms of rank. Of course, you should know how to compute determinants, and you may want to understand some of the shortcuts in computing determinants as well. Of course, this does give us back to row reductions and elementary row operations. Those are important. They will show up the entire semester. But again, you don't want to only rely on those. If those are the only things you know on this class, then you really don't know linear algebra. So of course we can use row reduction to simplify our determinant calculations. So it's certainly going to be helpful for that. And then make sure you know the applications that we were talking about. The polynomial, solving for polynomials. Again, that's solving systems of linear equations. There might be a problem like that on the exam. Kramer's rule you should know, and you should also know the formula for inverses that we put on there. So I will have to cleverly write some problems to force you guys to use those methods, or at least use parts of those methods. So make sure you guys know that. And then eigenvectors from today. Any questions? Okay, so let's get into our eigenvector discussions. So the broader topic is called spectral theory. But for this course, it's mainly going to be eigenvectors and eigenvalues, which are pretty much the general gist of what spectral theory is, though once you get into higher math, if you need to, spectral theory kind of generalizes this process we've got going on with eigenvectors and eigenvalues. So the key thing we want to know is, given a linear transformation, so in particular, it's going to be a linear transformation that doesn't change the dimension. So from Rn to Rn, one question we kind of want to ask is, I'll put it in quotes, what direction or what directions does information propagate under T? Another way of phrasing this is, are there vectors that are invariant when acted upon by T? So geometrically, what's going on is we've seen that linear transformations, especially invertible linear transformations, correspond to a change of bases, really. It's like mapping one basis to another basis. And it kind of just changes the grid of our space. Changes the way we are looking at and measuring the space in some sense. And so we know that these vectors that a linear transformation can change. So if we typically start with our E1 and E2, we can change those vectors to almost any other combination. And then, so sometimes our E1 might come here, and then our E2 might come, let's say, somewhere here. So they can flip, twist, and rotate. And of course, in higher dimensions, more complicated things can happen. So the word eigen means characteristic in German. So that's where it comes from. And so in some sense, if we have a linear transformation that is transforming our space, it's transforming our grid, but maybe the original grid we were looking at wasn't quite right because things are twisting and flipping and the bases are transforming. But maybe there were certain combinations of those basis vectors, namely any other vector, some other vector in the space, where the linear transformation actually didn't change that direction. So in some sense, it's kind of like, let's give an example. Let's say we know our linear transformation from R2 to R2, where our F is just a flip. So what is this guy doing? This guy is taking our standard basis elements, E1 and E2, and it's changing it to E1 and, well, now negative E2. I'm sorry, so up here, this should be the image of T1, T of E1 and T of E2. And so we notice that E1 didn't change. And because of the linearity of the transformation, that entire line stays the same. that dimension hasn't changed under the image of our transformation. So in some sense, that's kind of, it's good in some sense. It's kind of what we want to measure. We want to find these types of dimensions for arbitrary linear transformations. It is characteristic, we say, of that linear transformation because that dimension isn't changed. So this dimension sort of is tied in characteristically. It's a very characteristic dimension that is tied intrinsically to this linear transformation f. Now, this kind of brings up some extra thoughts, though. Now, it's not just the direction. It's not just E1, not just that one vector. It's that it is the entire dimension, i.e. any vector that is a scalar multiple of E1. So I'm going to start using lambda as our scalars. It's pretty common to use lambda or t's. We've been using t's a lot, t's and s's, little s's for scalars. But as you get into eigenvectors, I think common to use lambda. The book uses x's. I don't quite want to use x's for our eigenvectors and eigenvalues. So meaning if we have any vector v that is a scalar multiple of e, then f of this vector isn't going to change. Any point on that line isn't going to change. That dimension stays where it is. But, well, what's happening to the other dimension? If we redraw it, let me add some color here. So here is our E1, and here's our E2. Which map to E1, T of E1, and then downward as our T of E2. Well, our other dimension which is, of course, going to be the span of our E2. Well, what's going to happen to that? Well, f of E2 just gives us negative of E2. Meaning, well, if we let's call the span of E2 V. It is a subvector space. The span of E2 is going to give us the vertical line. This will give us the y-axis, right? Any scalar combination of E2 is going to be on that line. And so in that whole dimension, that whole direction, if we're looking at not just our basis element in particular, but that direction, that dimension as a whole, where is that dimension going to be mapped under the operation of our linear transformation? Well, it's just going to take that whole dimension and flip it. But it's going to remain the same. I.e. the dimension. I should maybe refrain from using the word dimension since, I mean, this is kind of like the spatial dimension. Of course, usually we use the word dimension as just the numerical value of the number of independent spatial dimensions. A little bit redundancy. So i.e. the dimension, or the better terminology, the subspace, particularly the 1D subspace, spanned by E2 is invariant under F. Meaning that if we just look at that subspace and the image of that subspace under the operation of this linear transformation, it doesn't change as a whole. It might flip. What else could happen? So if we have, let's draw a little bit broader picture here. Let's try to draw a three-dimensional space. And suppose we have some line that goes through the origin, so it defines a subspace, and we can give it any sort of vector v. We might change around and rotate and flip and change the space around v, but ultimately what we are looking for is these specific types of vectors, these specific directions where the subspace that they span isn't changed under our linear transformation. Now, it might be, and actually here, let's stretch it a little bit. Let's say this was our vector v, but t of v still maintains its direction, but it could be stretched. It could be pointing in the opposite direction. But that doesn't quite matter, right? Because if we look at the all scalar combinations of v, look at the entire line as a whole, well, whether we stretch that line, we could twist that line, or whether we flip that line backwards, it's not going to change the line as a whole. So this is essentially what eigenvectors are. So eigenvectors are directions whose subspaces they define. Meaning if I pick any vector, we can define a subspace from that one vector. Just take all scalar multiples of that one vector, and boom, we have a subspace. So this was we did a few examples like this when we were first learning subspaces. That any given vector, any given direction, if I define all scalar combinations of that vector, it defines a one-dimensional subspace R invariant under the image of a given transformation. So formally, let's develop the mathematics now and the correct language we want to speak of this under. Sorry, was anyone still writing? I kind of pulled that away a little quickly. So what does this mean mathematically, and how can we state that in mathematical terms? This means, so let's formally define it, given a linear transformation between Rn to Rn, an eigenvector of t is a vector we'll call it V in Rn, such that, well, what's going to happen when we apply t to this vector? It has to be in the same direction. So just as we saw with that opening example, it could flip the vector. We can get a different vector overall, but it just has to be in the same direction. And if it's in the same direction, it means it has to be a scalar multiple of that same vector. So for some scalar lambda in our real numbers. So it can stretch it, it can flip it. If we were using complex numbers, you could kind of think of a twist or a rotation in it, but we're not going to get into complex numbers. So right now you kind of just think of our lambda, it could shrink it, it could stretch it, or if lambda is negative, it'll flip it in the opposite direction. But overall, it will maintain in that same subspace. And moreover, we call the stretch, or whatever factor that comes out in front, is what we call the eigenvalue. Called the eigenvalue. We can call it the eigenvalue of V, or we could say associated to V, or sometimes we just say, so let me kind of put all of these in quotes. It's called the eigenvalue of V, of eigenvalue associated to V. Sometimes when we're just looking at eigenvalues in general, we also just call it an eigenvalue of T, of the linear transformation. So our idea is that these linear transformations, there's going to be certain vectors where it's not going to change the direction of the vector. And then there's going to be certain characteristic scaling factors for each of these directions. And these characteristic scaling factors are intrinsic to the linear transformation itself. So our question is, how do we find them?
I have one question about the eigenvectors and eigenvalues. Is it only for cases where it's like Rn to Rn, or could you have an eigenvector and eigenvalue if you had a transformation from like R3 to R2, where at least one of those vectors was preserved, like it wasn't such that like the image of one of the vectors was still in the span of the original vector?
Yeah, you got to be careful with that. I haven't seen it much. I think you could generalize it. In general, like if you're going from R3 to R2, it'd be kind of hard because there's not necessarily, I mean, there is a canonical way of mapping R3 to R2 as long as you kind of have built R3 out of maybe a canonical two-dimensional plane. But the problem is when you're mapping R3 to R2, are you mapping R3 onto the XY plane? Are you mapping R3 onto the YZ plane? And so you'd have to be careful, especially going from a higher dimension to a lower dimension in that regards. Going from a lower dimension to a higher dimension might make a little bit more sense. So this is actually a good question, a good kind of just thought process of what's going on behind here. If we have, so R3 to R2, a higher dimension to a lower dimension, well, what is the canonical? So canonical means like the absolute, or sort of the almost like the gospel way of doing it. The canonical part of R3 that corresponds R2. And there really isn't one unless you sort of a priori define it in some way. Like you would have to have R3 and your transformation, well, it would go to R2. And so the only vectors that could be preserved, or the only subspaces of R3 that could really be preserved, well, you might consider lines in the XY plane that then map to the same line.
So yeah, that was kind of my question. Is if on like a vector that would map to that same line, like if you just had a transformation that basically just mapped the vector XYZ to the vector XY, so it like preserves X and Y, would you have eigenvectors for that?
I mean, you'd have to be careful with how you develop that, because this isn't necessarily right. If this is V and then this is T of V, is it necessarily the case that T of V is a scalar multiple of V?
Okay, yeah, I get that. Thank you.
Right? Because in the other problem is here we have X, Y, Z, but Z can vary. This is going to map a lot of different vectors. This is actually a natural projection map, right? So if I have like 1, 1, 10, it's going to map to 1, 1. But if I change that 10, it's actually going to change the vector here. 1, 1, 30 is still going to map to 1, 1. So there's not a like canonical way of defining it unless you are particular about what this value of Z is, unless we force Z to be 0 maybe. Then you might be able to consider that. But there, as soon as you start to get into this choice of which specific subspaces and which canonical choices of how we're mapping what to what, we lose a little bit of the rigor. It becomes non-canonical because we have to choose what we would define as an eigenvector or an eigenvalue. You can, in some sense, do it from a lower dimension to a higher dimension as long as you define a canonical injective, which is a little more natural to do, because especially the way you build up infinite dimensional spaces, you can talk about eigenvectors and eigenvalues of linear transformations on infinite dimensional spaces, which you can in some sense build up from smaller dimensional spaces. So that might be possible, but it's a bit beyond the scope of our discussion here.
Okay, thank you.
So good question though. And so let's get back to our question of, well, now how do we find these? So we do kind of want to stick with even dimensions on the image and domain. So same dimensions. And then now how do we find these characteristic directions, these characteristic subspaces, and the eigenvectors and values that define them corresponding to a given transformation? So it's going to be coming back to this defining equation here. So if we have T of V equals lambda V, we're looking to solve a system of equations like this, right? We like to represent our linear transformations as matrices. So maybe through the matrix representation, we can maybe work with this defining equation a little bit. So let's start with this a little bit, and then we'll maybe throw in the matrix. So what we're going to do is, this is just saying that T acting on V minus lambda acting on V is equal to 0. And we can actually phrase this in terms of operations now. This is lambda times the identity acting on V. Since the identity acting on a vector isn't going to change it. And now since we have two matrix or two transformations operating on the same vector, our distribution property applies, namely that T minus lambda I acting on V is equal to 0. In other words, if we use A as the matrix associated with T, and then subtract off lambda times the identity, that acting on V should be 0. Now, one thing to note, I forgot to specify, and this is important, that the vectors we're looking for should be non-zero. If we have the 0 vector, of course, any transformation acting on the 0 vector gives 0 times that vector. So that's kind of trivial. That's a dimension that is 0 dimensional, goes to 0 dimensional. We are looking for actual full dimensions that end up as a scalar multiple of the same dimension. So a non-zero vector. And so moreover, what does this imply? So this implies since V is non-zero, that, well, what do we have? We have a non-zero vector. This is now a matrix or a linear transformation that sends some non-zero vector to 0. So namely, the kernel of that transformation is non-zero. Other ways we can phrase that, if we want to use our transformation notation, t minus lambda I is not injective. Other equivalent statements, t minus lambda I. So whether you want to use t or the matrix, same thing in description. T is not injective. Then what does that mean? That means the rank of t minus lambda I is not equal to n. It also means, so let's put these double arrow, since all of these imply the same thing. That t minus lambda I is not invertible So all of these things are equivalent, and we even have one more now useful tool that can tell us of this. So of course, computing bases for the kernel, I could now maybe compute this matrix, try to find a basis for the kernel or find elements in the kernel. These are examples we've done before. That would give us a direction of solving for these lambdas. Kind of along the same lines in terms of injectivity and maybe rank. The rank one's going to be a little hard. Why is rank hard? Because so far with rank, we've liked to row reduce. And what's the problem with row reducing? As I was mentioning a bit yesterday, we have this lambda in there. Whenever we have variables in our matrix, it's going to be hard to row reduce. And what was our tool instead that we used with variables in the matrix? Our determinant. So I'll go back to our matrix notation. Since determinant, we usually mean the determinant of a matrix. Of course, if it's written the determinant of a transformation, we mean the determinant of the matrix associated with the transformation. And since the rank is not n, if we were capable of row reducing this guy, that means we should get a 0 row. So our determinant is going to be 0 whenever we have a non-invertible matrix. So this gives us a very powerful tool towards solving this, answering this question of how do we find eigenvectors and eigenvalues? Okay, so let's take a look. Get some more paper. So solving the equation, the determinant of the matrix associated with T minus lambda is the value we're solving for times the identity equals 0, gives us the values of lambda, i.e. the eigenvalues of T. This is going to be our first step. Unfortunately, as soon as we use determinants, we're going from matrices to scalars, right? Determinant takes matrices and spits out a number. And we have some interpretations on what that number is based on our work and discussions over the past couple of days. But we also have an understanding of this tool of determinants, and at least in some sense of what it means in terms of invertibility and rank, particularly when the determinant is 0. And so we're using that fact to help us set up an equation to solve for these values of lambda. Unfortunately, at this point, we don't have any information on the actual directions, the eigenvectors associated with the eigenvalues. But if we can at least start with the eigenvalues, maybe then we can set up a system of linear equations following any such equation in our line of thinking to solve for the vectors v. So let's go through some of these examples. So, excuse me. So we opened with one example. I actually kind of forgot to mention, I wanted to open with both of the transformations of the plane. So let's take a look at both of these. Let's have f given by our flip. And our rotation matrix given by our standard rotation matrix. Now, the flip we talked about, and we have kind of intuitive sense, it actually preserves both of these standard basis directions. E1 doesn't change at all, and E2 just flips back and forth. So that one's going to be pretty easy. And it will match our geometric intuition. What's going on with the rotation matrix? Well, if you kind of think about how things are rotating, it's going to send E1 and E2. Well, it's just going to rotate them. Around. And so does that preserve any direction? Like if you kind of think of any direction under a rotation matrix, everything is rotating. So is any subspace really preserved under that transformation? It doesn't quite look like it. So how do we prove that mathematically? Well, now we got a little bit of tools we can kind of chase out. So let's go through this process for some of these easy examples. And then maybe we'll take a look at just more general examples. So f was pretty easy. If we want, again, f minus lambda times the identity times a vector should give us 0, then I know that the determinant of f minus lambda times the identity is going to be 0. So all you got to do is take our matrix associated with f. We are subtracting off lambda times the identity just means we got lambdas on the diagonal. So identity just has 1s on the diagonal. If we multiply that by lambda, of course, 0 times lambda gives us 0. All the 1s times lambda give us lambda. And so now we are looking at this matrix, and we want to compute the determinant. 1 minus lambda, we've got zeros, and then I've got minus 1 minus lambda. Ends up being a pretty easy determinant. And I would say if it's already factored, keep it factored, right? We're trying to solve now a polynomial equation. So some of these can get a little hairy, especially as we get 3 dimensions, 4 dimensions. Because solving polynomials for their roots is going to be a little difficult. So we'll see why polynomials are coming out of this. Of course, we just have powers of lambda. And then since all of the numbers are constants in our matrices, in our linear transformations, we're essentially just going to get multiples of lambda plus or minus constants, and constants times those multiples of lambda. So ultimately, after we're computing these determinants, it boils down to some sort of polynomial equation equal to 0. And now we are looking for polynomial roots. So if you thought you could get away from all your pre-calc knowledge, think again. Finding roots of polynomials comes up a lot. See it here in linear algebra. You would see it again in algebra, abstract algebra. So of course, solving these, 1 minus lambda equals 0, minus 1 minus lambda equals 0, setting each term equal to 0, lambda equals 1, lambda equals minus 1. So we know these are our 2 eigenvalues associated with f. Let's take a look at R real quick, and then we'll go into finding the eigenvectors corresponding to it. So we're going to have our cosine minus sine, sine, cosine, minus our lambdas. And so we are trying to compute our determinant of this matrix. So what are we going to get? We're going to get cosine theta minus lambda, cosine theta minus lambda. So that's squared minus negative sine times sine will give us a positive sine squared theta here. And we want to set that equal to 0. So let's see if we can solve this. Sometimes, especially with trig functions, could end up being solvable, could not, since we have cosine theta minus lambda squared, cosine theta minus 2 lambda cosine theta, plus lambda squared, plus sine squared, equals 0. Cosine squared plus sine squared is going to give us 1, so we'll have lambda squared minus 2 lambda cosine theta plus 1 equals 0. And so now the question is, what are the values of lambda? What are the eigenvalues in this case? What do we got to use? Quadratic formula. So lambda is 2 lambda cosine theta minus the square root of 4 lambda squared.
Wait, wouldn't it just be 2 cosine theta?
Yeah, 2 cosine theta. Sorry, I'm confusing which variable is what. 2 cosine theta minus square root of 4 cosine squared theta. Square root of 4 minus cosine squared theta minus 4ac. So 4 times 1 times 1 all over 2. Now, what does this tell us? This is 4 times cosine squared theta minus 1 all over 2. And what about cosine squared theta minus 1? what do we want to say about that? It's underneath the square root, so we could, here, 2 cosine theta minus 2, square root of cosine squared theta minus 1. How do we determine the solutions to a quadratic equation, especially over the real numbers? We are looking at the discriminant, so the term underneath the square root, which we can reduce down to cosine squared minus 1 is only going to be greater than or equal to 0 when theta is integer multiples of pi. Cosine theta in general is less than or equal to 1. Right? I guess if we were to solve it properly here, we've got cosine squared theta is greater than or equal to positive 1, but I know that cosine has to be less than or equal to 1. So meaning it's never going to be greater than 1. The only solutions we're going to have is when cosine is squared is equal to 1, which means cosine is equal to 1, or cosine theta is equal to minus 1. So that's going to happen at multiples of 2 pi and odd multiples of pi. Meaning our rotation only has eigenvalues. For this class, we're only going to look at real numbers since we haven't been working with complex numbers. It only has real eigenvalues when theta is some integer. Meaning that if we rotate just some arbitrary amount through the plane, there are no fixed directions. The only time we have fixed directions is when we either rotate pi. So here, let's do it this way. If we rotate a multiple of 2 pi, well, what do we get? We get the identity. Right? If I rotate everything around a full circle, well, we get the identity. Or if we rotate around pi, cosine of pi is now minus 1. Cosine of pi is minus 1 again. So this is just rotating the plane halfway around. What are we going to get eigenvalues here? Our eigenvalues are going to be negative 1. So go back to that equation here. Or even here, might be a little easier. If our theta, we've shown that our theta has to be pi or 2 pi, essentially, or some multiples of that. If theta is 2 pi, well, then I have lambda squared minus 2 lambda plus 1. Easy factoring. Should be able to show that lambda is negative 1, lambda minus 1 squared is that polynomial. And then likewise, if lambda is pi, we will get just a negative here. So essentially the same factor, lambda plus 1 squared, will give us the eigenvalues of negative 1. Geometrically, hopefully that's making sense, because if we draw the picture again, right, if we start with our standard basis vectors, and we think of just any vector, any combination of vectors, if we just arbitrarily rotate them, well, we're changing the direction of all the vectors. When are we going to have an invariant subspace? Well, we kind of need those lines, any line, to end up on itself. And so if we kind of take the x-axis and if we rotate it pi 180 degrees, well, we'll still get the x-axis. Likewise, the y-axis rotated 180 degrees will still give us the y-axis. We'll expand upon this a little bit more as we talk about the eigenspaces associated to a given eigenvalue. Right now, we're not quite there yet. We'll probably get there tomorrow. Because one thing to note is that, well, if this is our transformation, it actually doesn't matter. Any line we draw, if I apply this rotation 180 degrees, it's still going to give me the same line, meaning every direction in this case is actually like a characteristic direction. So we'll build up to that. We'll talk about what's going on there. Let's kind of get back to our basic examples and then maybe check some more computations with this guy. So what have we seen? We've seen, as we kind of expected, that with our flip, we have two eigenvalues. We found an eigenvalue of 1 and -1. With our rotations, we realize, well, there's no eigenvalues unless we are rotating 180 degrees or 360 degrees. And in that case, both of the eigenvalues are the same. We'll come back to that example. Let's kind of focus on what's going on with f at the moment. F is a little more easier to start with in terms of thinking about our directions. So when we drew the picture and we think about f, one of the directions we should expect is just E1. That should be an eigenvector associated to f. Because we know that if I flip, it's not flipping at all. It stays exactly the same, meaning f of E1 gives us E1. So this is 1 times our E1. So we should expect this E1 to be associated with this eigenvalue of 1. And likewise, what happened to our E2? It just, that is the dimension that we flipped. So our scalar multiple of E2 ends up being E2. So this is kind of a guess and check way to do it. We could actually compute that. We could compute f of E1, 1, 0, and we could show that f of E1 still gives us E1. And of course, f of 0, 1 is going to give us 0, -1. And so the eigenvalue associated with E2 is going to be -1. Sorry, I'm off screen there a little bit. But let's go through the mathematical procedure now to check our intuition, because we do want to generalize this to different matrices, different transformations. We found our eigenvalues. How do we actually prove and find the eigenvectors now? So nicely enough with f, we have this intuition in mind. We know what we should get, so this will be a good way to check our answers. Let's go ahead and rewrite our f. And we are looking for f acting on v equal to v itself. In other words, we're looking for an equation. So there's a couple ways you could set this up. You could either set it up as this equation, or we could set it up with the f minus lambda times the identity of v equals 0. They are equivalent. So what do I mean by this? So essentially what we're getting, we're going to write v in component form. So pick your constants, v1, v2, or you can pick x and y if we're in 2 dimensions. And so now I have a system of linear equations that looks like this. Careful with systems of linear equations like this, though, right? It's hard to solve because here we have x's and y's. Typically, when we use our row reductions to solve systems of linear equations, right, we ignore this x, y, and then append these guys in an extra column in our matrix for row reduction. So might be better to work with this equation. Namely, what this is going to say is 1 minus lambda times 0, 0, minus 1 minus lambda times our v times xy is equal to 0, 0. And now this one, since my constant vector is constants, this b, we can use our row reductions to solve this. And I should say, moreover, since we know our values of lambda at this point, so we're going to plug in our values of lambda and then solve from there. So we'll start with lambda equals 1. We are trying to solve, well, 1 minus 1, that'll give us a 0, minus 1, xy equaling 0, 0. And so, of course, this simply comes down to taking a look at our augmented matrix and solving it via your favorite technique, row reductions, LU factorization, what have you. Nicely enough, it's already factored. So we get the top row of zeros, and then our bottom row essentially says that, so remember, this is our x and this is our y. So the bottom row says minus 2y equals 0. So our y has to be 0. X can be anything. Now, seems a little scary. We should arrive at E1, right? But this is just telling us that our vector v has to be of this form, since x can be anything. And moreover, right, our idea isn't necessarily that we have a strict vector that is being preserved under this transformation. It's not just that E1 was the only vector being preserved. It's that any scalar multiple is an eigenvector associated to that eigenvalue. So choose anything for x. If you want to pick your basis element, typically nice to choose basis elements that are of length 1. That's actually the next section. Once we get into orthogonality in the Gram-Schmidt process, we've talked about basis vectors, how to create bases and linear independence, but we haven't worried too much about what are called orthonormal basis vectors, where we create bases that are mutually orthogonal, mutually parallel, and of length 1. Not important. You don't have to choose x to be 1, or especially once we'll find other dimensions and other directions for different transformations where, again, the solutions aren't going to be unique, because an eigenvector defines an entire dimension that will be preserved under that. So really what we're looking at is scalar multiples of E1, meaning any vector in the direction of E1 is going to correspond to an eigenvalue of 1. So answer-wise, I would say you could leave it something like this if you want, and you could even write x and r. Or if you just want to pick 1, or if you just want to pick v equal to 1, 0, perfectly fine. You could even throw your favorite number there in that top position. Since it's implied by our work that whatever eigenvector you find and whatever eigenvector you choose, of course, if we take scalar multiples of that eigenvector, right, if we did f acting on x times E1, well, I know that's just going to be x times f acting on E1, since we can pull out scalars from linear transformations. And of course, we've computed f of E1 and shown that that's just E1. So that is certainly 1 times the vector we started with. So we get that same eigenvalue. Likewise, for lambda equal -1, we've got our 1 minus -1, minus 1 minus -1, times, we could use xy again. You may want to use, let's not use u and v. Let's use s and t. So this is for our second eigenvalue. Maybe we'll call that whole vector v2. We solve again. And so in this case, we get our top coordinate has to be 0, and then the bottom coordinate can be anything. So we can pick our v2 equal to 0, 1. And we know that this will have eigenvalue -1, corresponding to our transformation. Questions on that? Okay, so we've got quite a bit to get through. Let's try to do some more examples with the time we have remaining, something that's a little more non-trivial. So find eigenvectors and values for our transformation given by this matrix. So R2 to R2. And so again, we're looking for the determinant of A minus lambda I, which is going to be -5 minus lambda, 4 minus lambda. So just subtract off lambda from the diagonals, compute our determinant, and unfortunately, it can get a little wonky. And that'll be a plus 14, so minus 2 times -7. So of course, we're setting that determinant equal to 0. And we've got work to do. We've just got to do all the arithmetic, all the multiplications. Let's see, I've got a lambda squared. We've got -4 lambda and +5 lambda. So plus lambda and a -20 plus 14. Lambda squared plus lambda -6. So +3 and -2 for our factors give us a -3 and a +2 for our eigenvalues. Everyone with me? We know those are the eigenvalues. Now we want to find the eigenvectors. So let's do lambda equals -3 first. What we want to do is take our matrix, so -5, and now instead of minus lambda, let's subtract off the actual value of lambdas we found. And then 4 minus our -3 times our first eigenvector, give it coordinates x, y, and we know that that should go to 0. So we are trying to solve -5 plus 3 minus 2, 2, -7, and 4 plus 3 gives us a 7. And then we just augment by zeros. So nicely enough, when we have this type of system of linear equations, especially when setting it equal to 0, it's always the homogeneous system of linear equations. So, I mean, we can almost always ignore that last row since they're never going to, or last column, never going to change from 0. And what's going to happen when we solve this? If we factor out the corresponding components, whenever we do these row reductions, we should always get at least one row of zeros. It is possible to get more than one row of zeros. But I think for most of our elementary examples, we should always get at least one row of zeros because we are expecting a one-dimensional solution, right? There isn't just one specific vector. It is all scalar multiples of that vector, meaning we have a one parameter family of solutions. So we should always have one free parameter. And so, of course, remember x and y, this just says minus x plus y equals 0. So x equals y is our only constraint. So we could say choose v1 equal to 1, 1. Or any scalar multiples of that. You could choose 1/2, 1/2. You could choose 10, 10. You could choose -1, -1. As long as we are in that same direction as this vector, all essentially corresponding to the same dimension that corresponds to this -3 eigenvalue. And if we check, our -5, 2, -7, 4 times 1, 1. So the key thing is that we should get back -3 times the vector we chose. So we should get back -3, -3. And if we compute that, we'll have -5 plus 2 in the first row. And in the second row, -7 plus 4. And we see we found it correctly. So -3 times the vector we chose. Let's do the other eigenvalue now. Our other eigenvalue was 2, I believe, yeah? Yep. So for lambda equal to 2, we'll have -5 minus 2. Off diagonals stay the same. 4 minus 2. I'm going to use the same variables, but this will be our v2. So the second eigenvector. And the eigenvector associated with eigenvalue of 2. And so what is our equation going to be? -7, 2, -7, 2. Append by zeros. Easy enough system to solve. What does this tell us? Gives us one equation relating x and y. -7x is -2y. Or maybe we can get rid of the negatives. -7x equals 2y. So that means we can choose. It's a good choice for our second vector. So pick any numbers. You can pick 1 for x, solve for y. A little bit of arithmetic and some numerical work can hopefully get you to some nicer values of x and y. Namely, what happens if I choose x as 2? Whenever you have a coprime numbers like 7 and 2, like 7x equals 2y, pick the opposite values for the opposite variable. So, right, 7's attached to 2, or 7's attached to x. Pick 2 for x. What's y going to be? Y will have to be 7. Again, you could normalize that, or if you choose x is equal to 1, y is equal to 7 halves, it would work just as well. But if you want to pick whole numbers, that's kind of an easy way when you get equations like this, because we'll have 7 times 2 equals 2 times 7. And then, of course, we check. Minus 5, 2, minus 7, and 4. Acting on 2, 7. Now, our eigenvalue is 2. So we should get 2 times this guy. We should get 4, 14. So minus 5 times 2 is 10, negative 10, plus 14. So far, so good. Negative 14 plus 28. So what do we get? Exactly what we want. Any questions? All right, let's do one more. We'll try to go through it quickly. This one's going to be hard. We probably won't finish it, but I want to do a 3x3 because it's going to get chaotic. And then let's see, tomorrow we need to talk about 0 eigenvalues. So 0 eigenvalues aren't too hard. It's really just the kernel. If I have non-zero vectors that are killed off, any non-zero vector that maps to 0, you can kind of think of just being a 0 eigenvalue. And then we'll get into similar matrices, which gets us into some row operations and a little bit of tricks in terms of finding some of these eigenvalues when the matrices get complicated. Because if we have a 3x3 matrix, let's see what happens. So I think this is an example in the book. We've got 5 minus 10 minus 5, 2, 14, 2, minus 4, minus 8, 6. So please look over all of these examples in the book. They are very good examples and really what I'm trying to base a lot of these problems off of. And the nice thing about examples in the book is they don't actually do all of the steps for you. So you have to fill in all the steps, but they give you like the answers. So if you want extra practice, a lot of the examples that are already given in the book, good practice. So we subtract off lambda times the identity and take the determinant, and we want to set it equal to 0. So 5 minus lambda. Unfortunately, all these other values are going to stay the same. And there's a lot of them. So that's going to be a lot to work with, a lot to calculate. Computer determinant, set it equal to 0. And again, unfortunately, because we don't have a lot of zeros in here, expanding the determinant is not the easiest. Yeah, I think we're just going to have to plug and chug. Ready? So we've got a few minutes. Let's get started. So let's expand upon, I want to do the first column. These numbers seem the smallest. And I always kind of like to start with one of the lambdas to expand upon. I think, yeah, first column's going to, looks like it has the smallest numbers. So we'll have 5 minus lambda times the determinant of our minor. So lambda 2 minus 8, 6 minus lambda. Then we'll have minus 2 times the determinant of minus 10, minus 5, minus 8, 6 minus lambda. And then we've got plus a negative 4 times minus 10, minus 5, 14 minus lambda, and 2. And now we got to compute all the other determinants. 5 minus lambda times 14 minus lambda times 6 minus lambda minus 2 times negative 8 is plus 16. Minus 2 times, we'll have minus 10, 6 minus lambda, minus negative 5 times negative 8 gives us just 5 times 8. And then plus a minus 4 times minus 10 times 2 is minus 20 minus negative 5 and 14 minus lambda. Let's simplify inside each of the brackets first and then multiply things out. So in the first one, 5 minus lambda, I'm going to, do we want to keep that as it is for now? Nah, let's go ahead and just start expanding things. Unfortunately, because we have lambdas and powers of lambda in each of these, we're going to have to just multiply everything out. All right, 6 times 14 is what, 84. We'll have minus 14 and minus 6, so minus 20 lambda. And then plus lambda squared plus 16. It's that one. We'll have, I'm just going to write this as plus a minus 2. I'll just distribute that minus just to remember that guy. We'll have minus 60 plus 10 lambda minus, that's a 5 times 8, which is 40. And then plus a minus 4. We'll have minus 20, and then this is, distribute that minus sign, making it a positive 5, times 14 is 70, minus 5 lambda. Everyone with me? So these two are now not going to be too bad. This one's going to be the harder one. Let's go ahead and, so 5 minus lambda. Let's simplify the inside. We've got a lambda squared minus 20 lambda. 16 and 84, nicely enough. Good old 100. We will have plus, I'm going to keep parentheses around these, but distribute. So we'll have 120 minus 20 lambda. Maybe we can combine those. So minus 60 and minus 40 is minus 100 times minus 2 gives us positive 200. And then plus, what's this last one going to be? So that's going to be minus 50. Excuse me, positive 50 times negative 4 gives us a negative 200. Negative 4 times negative 5 gives us a positive 20 lambda. Now, these two terms are going to cancel. 200s are going to cancel. Minus 20 lambda plus 20 lambda. Great. So now all we have to do is work with that term. Let's keep that as it is because it's already factored. And we, of course, want to set that determinant equal to 0. So our equation now, we've reduced it down to, we'll start with this tomorrow. We've shown our 5 minus lambda times lambda squared minus 20 lambda plus 100 equals 0. So this is our defining equation. We also call this the characteristic equation. So this will give us our solutions for lambda. Nicely enough, it's already factored. So this factor we can solve for. And then now we might have to use quadratic formula or factor this guy to solve the other values of lambda. Once we find the values of lambda, we will then find the corresponding eigenvectors associated with those eigenvalues. So we'll jump into that tomorrow. Any questions?